around in a circle, there are a few things that we can define about that circle. One is that one revolution is 2 pi radians, which is also 360 degrees. Okay. The distance along the edge, the distance for one complete revolution is known as the what? What is that fancy name? Circumference. And how do we solve for circumference? Do you remember that equation or something? 2 pi r or pi d. I like the 2 pi r version. All right, so let's hop back over here to our ladybug. And let's let the ladybug roll here. And if I hit play, now what if instead of going all the way around the circle, the ladybug goes only part of the way? Was there still a distance that the ladybug covered? Yeah, what was that distance called in math class? When you, oh, arc. Do you remember how to solve for the arc distance or arc length? You can make a ratio. Does anybody remember using the S for arc length? S equals r theta. That's right. And if we go all the way around the circle, what's theta going to be? 360 degrees, but we have to use radians. So it would be r times 2 pi. Does that look like the circumference? Circumference is a special case of the arc length. So if you can remember the circumference equation, 2 pi r, where 2 pi is the theta and r is the radius, then you can always remember the arc length equation. Because it's the angle times the distance, or the radius. Yay! Okay. So, now let's look at our ladybug again. Ladybug goes round and round. So, when we only go part way round, we've traced out some change. There's been some arc length, and we've also swept through an angle. Okay? And does that take time? Yeah, it sure does. So as this ladybug, or as something moves in a circle, okay, it goes through a change in angular position over time. Change in angular position over time. And what is something that's like a change in something over time that's called a rate? Very good. That's a rate. And this is position over time. And what was linear position over time? Velocity. So this is angular position over time. So what do you think it is? Angular velocity. God, y'all are catching on. All right. And the symbol we use for angular velocity or angular speed is an omega. That's a Greek letter. I'm saying omega. On kindergarten paper, it would look like this. There's that middle dotted line, and you would start here and go up like that. An uppercase omega, if you're confused, would look like that. Okay? Those are our omegas. So the omega is the angular speed or velocity. Now, what would its unit be? Well, let's see. What is theta going to be measured in? What unit do we have to measure theta in? Radians. Per, what's this, second? Now, truly, radian is a non-unit unit. I know that sounds crazy, doesn't it? It's something we say to make us feel good, because we say like 360 degrees. You want to finish it off, but really it's a non-unit unit. So it's the same thing as 1 over seconds, or seconds to the -1. Those are all reasonable, acceptable units for the angular speed. I like to put radians per second because it reminds me what I divided by.